Welcome back to day 2 of distance learning. I assume you guys are missing school as much as I am. Bet you never thought you'd say that. I miss school, but I do. Maybe you don't. I don't know. Maybe you love this. So let's get to it. This video is also going to be split into two pieces just like the other one. The first one is again going to be the lesson for today, and then the second one is going to be some example problems just to keep the overall file load down on my computer. So here we go. Day 93. Now we're done with our area stuff, and we're going to get into something called volumes by cross sections. We're getting three-dimensional today. However, before we start, we have a quick assignment check to make sure that you understood what you learned last class. So there are two problems here. You're going to have 10 minutes to complete this, and you'll need to pause the video and then do it, and then unpause after to see how you did. Your goal on the first problem is, of course, to find the area of the shaded region. You actually have to find the area. And then the second one is calculator active, so hopefully you have that ready. And your goal is just to find the area of R. So go ahead and pause the video, take 10 minutes, try it, and then unpause the video to see how I did it and see if your answers were correct. Ready, set, pause. Alright, hopefully you've had enough time to get these problems done. I just wanted to show you my setup. This to me looks like our first problem here is a simple top equation minus bottom equation. So we're just going to have to go the integral of my top equation, that looks like the red line, which is 4, minus the bottom equation, in this case, which is x squared, and then we have to do this with respect to x. Now the problem is, where do we do our limits of integration? Well, hopefully you can look at this and see that these two cross. If this y value is 4, what does x have to be to get 4? Hopefully we see that's 2 and negative 2. So I need to integrate from an x value of negative 2 to an x value of 2. Let's do a little antiderivative practice. So we're going to end up getting 4x minus 1/3 x cubed from negative 2 to 2. Well, that was interesting. From negative 2 to 2. Then so I'll take some work up here, I think. We'll have to plug in 2 for our first one. That's going to give us 8 minus 1/3 of 2 cubed minus, and now we plug in negative 2, so that gives me negative 8 minus 1/3 of negative 2 cubed. And then you could actually stop here and you say, haha, I win. If you went a little further, I think we do 8 plus 8, which is 16. This is minus, let's see, 2 is minus 8/3. And then this one, this one's a little trickier. Negative 2 cubed is negative 8. Negative times negative is a positive, and then we subtract again, so minus another 8/3. So yeah, you can go further from there. I don't really feel like it, but if you got your answer, congratulations. 16 minus 16/3, whatever that may be. Alright, second one, calculator active this time, a little bit tricky again. I think you'll probably need to split this region R into two smaller regions, where the first region is actually pretty easy. This region in blue right here, I'm just going to do by using my tangent of x equation. Oof, easy for me to do there. There we go. My tangent of x equation. It's just the area from tangent of x to 0. So that one won't be too bad. My first integral, maybe I'll call this blue region like area 1. So area 1 is just going to be the integral from, well, it definitely crosses the x-axis at 0 to something, we'll get back there, of the graph of tangent of x minus 0 dx. Cool. The second region is a little bit weird. The second region now turns into, I'll do it in orange here, is actually just the second function, and we're just going to do top minus bottom. So I'm going to add on my second region here. Maybe I'll do it like this, a sub 2, and my second region is going to be the function 2 minus x cubed. That's my top function. My bottom function is 0 right here, so minus 0 dx. We have a couple issues though, and those issues are, where do these graphs cross? We need that x value, that's right here. And then also, where does 2 minus x cubed cross the x-axis? I can handle that without a calculator. Set the y to 0. X cubed equals 2, which tells us it crosses the x-axis at the cube root of 2. So I know at least I'm going to integrate from something to the cube root of 2. cube root of 2. I need to find where these two functions cross though, and that's really where our calculator's first going to come in handy. So first thing I want to do is, and I'll try this a different way, we're going to go ahead and graph. And on my graphing screen, I want to go ahead and graph my tangent. Oop, apparently I'm going to graph lots of things as it just goes everywhere here. Ha! Did it. As we're going to do, stop it. Awkward. We're going to do the tangent of x. Escape. Hey! Tangent of x. And then the second thing that we're going to need to graph was that 2 minus x cubed. Okay, and we can see our two regions down here, very nice. We need to figure out where they cross, so that's our menu, analyze graph, intersection, and I'm going to try not using the pen this time and see if that works. Lower bound, upper bound, we've done it. And it looks like they intersect at 0.902. However, as we found before, we want some more decimals on that. And in fact, I'm actually going to click into this. There we go. And I'm going to store that value for later use. I'm going to store it as A, I think. There we go. All right, so we stored that as A. That looks good, 0.902. And so we should probably show that over here too. Otherwise, they're going to say, where'd that weird value come from? So I'm going to show down here that 2 minus x cubed is equal to the tangent of x for an x value of, just remembering quickly, 0.902. And I'm going to go ahead and let A equal 0.902, just so I don't have to keep writing it. So now I can go from 0 to A, and from A to this. Those are my two regions, and then of course the total area is just those two regions added together. So going through, I'm just going to show this on the calculator quickly. We should remember that f1 is tangent, f2 is 2 minus x cubed. That might save us some time. So let's see, we need to integrate menu, calculus, and we need to go from 0 up to, and I can just type in A. Notice it should be bolded there. It's a little worrisome that it's not, but that's all right. Maybe it'll work in a second. From 0 to A, actually, let's check this. I don't want to do all this work. Is A equal to something? No, it's not. So something weird happened. Let's just fix that quickly. Click down, Control Store. We're going to store this as A. Second try. Is A bolded? There we go. Now we're back to it. Always good to check your work. All right. Menu, calculus, integral. We're going to go from 0 over to A. That's much better. And then the first function, if you remember, was our tangent of x. Well, tangent of x was in f1 of x. So instead of typing in tangent, you could, but I'm just going to type in f1. Notice it gets bold because there's something taking up that spot, f1 of x. Okay, and then at this point we need to add on a second integral. My second integral, calculus integral, is going to go from A up to the cube root this time. This one's going to be weird. Cube root, I want that 3 to go there, please. Ha! The cube root of 2, and the second function, which is in, I believe, f2 of x dx. Now we have our two integrals. We can hit enter, 0.7293. Alrighty. So there is our warm-up problems. Should have taken you about 10 minutes, give or take. Maybe you did it faster, maybe slower, but make sure you're comfortable with that. Now let's get into our new stuff. So our new stuff for today is we're going to go ahead and start creating three-dimensional objects using calculus. Now, first thing we need to remember is, what is three-dimensional? Well, we should know that a line is one-dimensional, right? And some sample units of one-dimensional might be one-dimensionality, might be meters or feet or anything like that. Okay. Now, let's picture some two-dimensional objects. Two-dimensional objects, we could have a triangle, a circle, a square, anything like that. These extend in two different dimensions. Think of them as axes. They extend in an x direction and a y direction. And in order to create units for one of these, you need two components. So oftentimes we see this in terms of area. So for example, some areas for two-dimensional shapes are always created by taking one dimension and multiplying it by another dimension. So for an example, a rectangle is the length times the width. Each of these is one-dimensional. You could have the length of a line times the width of a line, two dimensions, two directions if you want. You could also have a pi times a radius squared, so it's a radius times a radius, right? A radius goes in one direction, a radius goes in another direction. You multiply them together to get two dimensions. Three-dimensional objects, moving on then, are just two-dimensional objects that you multiply by another dimension. So if you wanted to turn a rectangle, length times width, into a prism or a cube, we just multiply by a third dimension, length times width times height. Each of these are one-dimensional taken alone, but if you multiply the three together, it creates a shape with three dimensions, three directions if you want. To create a cylinder from a circle, we take that radius times a radius and we again multiply by a height. Right? Essentially, we are taking a two-dimensional base and multiplying by a third dimension. And that's actually what we're doing today. Right? We're going to take a two-dimensional shape that we should know the area of. We're going to multiply by a height, and bam, we have made that three-dimensional. So here we go. Imagine we have a cylinder. And the question is, what sort of shape occurs if you cut that cylinder? Here's my attempt at a cylinder drawing. If you cut it horizontally. Well, horizontally would be like if you took a saw, right, and you like sawed apart the cylinder right here, and then you opened it up and you're like, oh, what shape is that? Well, hopefully you're like, well, if you tear a can in half, the bottom or the piece of the can that you're looking at would make a circle. Right? And this would be known as a horizontal cut. Okay? However, if you, and I should move that over here, if you took that same cylinder and instead of cutting it horizontally, now you cut it vertically, right? Here's my little, not the world's best artist here, but I hope we can figure that out. We might notice that if you cut a can straight up and down, this vertical cut, that when you turn the two faces to face each other, the two faces to face each other, that they actually make a rectangle here, which is kind of interesting. So, what we're going to do today is we're going to take a cross section, right? Where a cross section is like one of these cuts. And what we're going to do is once we have a cross section, once we have an area of one of these cuts, we're going to multiply by a third dimension and go from there. So steps, we first find the area of the cross section, which is two-dimensional. Would you agree both of these cross sections up here have two dimensions? Then we're going to give the cross section some infinitely small width, which of course we notate as dx or dy. And then lastly, we sum up every cross section we need to create a shape using an integral. Okay. Of course, you could sum cross sections indefinitely, right? They would go forever, so you need to give your integrals some boundaries, right? Now, what we're going to do really then is we are going to integrate some area function times dx, or it could be dy. And our area function is basically how do you find the area of one of these shapes. So hopefully you're good with area of two-dimensional shapes. But then what we're going to do to make this really cool is we're going to make our base a weird shape. And then we're going to build really nice areas off of it. So let's see what this looks like. First step, we're going to sketch the base of a solid, not the cross section, just the base of a solid that's bounded by these three lines, or they're not lines, curves or graphs. So pause the video, graph these as best as you can, then unpause it, and I will go ahead and show you how to do it. Alright, hopefully you have your graph done. I'm going to go ahead and get mine done right now, so let's take a look here. We're going to try to be somewhat accurate here. So let's take the easy ones first. Y equals 0. This would be like y equals 2. So y equals 0 is going to be the line that runs right here. And I'll go ahead and label that for us. That's y equals 0. X equals e. Well, where is e? E is 2.71828, all that fun stuff. So here's 1, 2, 3. So let's say that E is right about here. And here is my second line. This is going to be the line x equals E. And then last but not least, we need the graph of natural log of x, and that's one a lot of people forget how to graph. So to graph natural log of x, I just use the 3 things that we need to know. First, we should know that you can't plug in 0 or negative, so we won't need this side of the graph. Second, we should know that any log of 1 is 0. So that gives us the point 1 comma 0, that's right here. And then last but not least, we should know that the inverse of a natural log is e, and when you combine 2 inverses, it makes 1. So that is the point e comma 1. Oh, I need something on the y-axis now, so here is 1, 2, e comma 1 is right here. So natural log goes something like this. Okay, that makes it look like it's a perfect triangle. It's just curvy. There we go. So it's kind of our region here, and I'm going to outline it like so. Our region is this weird curvy triangle piece. Okay. Now, what we're going to do is on top of that weird curvy triangle case, we're going to go ahead and we're going to actually build some sort of really cool 3-dimensional shape. So what does that mean? Well, the first thing I'd like you to do is, using the space down here, I want you to redraw this. It can be a little less accurate, but I want you to really emphasize this shape. So what I mean is, if we're going to have this right here, and I really want to make sure that we get this cool looking shape. Here's 1, 2, here is E, and it's going to look something like, that's maybe too big, huh? Something like this. And then we have our E line that's coming right through here, and we've got our nice area that's in here. You shouldn't shade this in for now. Okay, so there is our area. Now, at this point, we're going to go ahead and look at some examples of what we're trying to do, but we should probably explain what we're trying to do first. What I'm going to do is, I'm going to take this area, and I'm going to use this area to create cross sections of squares to form a 3-dimensional shape, which seems kind of weird. So what we need to think of is, this base down here is something that we could stand on. Imagine it's like a dance floor. You can stand anywhere on this dance floor. You can stand right here, you can stand over here, great. And us, our heads, these people coming up off the dance floor, is what we're going to do with a whole bunch of squares. So we're going to go ahead and bring a whole bunch of squares off of the dance floor. Now, this is still kind of confusing. So what I'm going to do is open the program called Algebra and demonstrate what this is going to look like with squares. So what I have here is a really cool program called Algebra. Think geometry, algebra. It's a free program, and if anyone wants to play around with these files, these are free as well. Another AP Calculus teacher put them together. But what I'm going to do is show you a similar problem, not the same as we're doing, but similar, and I think it'll give you a good idea. So we talked about how we have this kind of dance floor over here. We've got the same idea here. It's this whole region that's graphed, or you can actually see the region right here. This is a 3-dimensional view. It's kind of a tricky view. I can play around here, but we should see our x-axis in red, the y-axis in green. And that's all we really need. Now, strangely, this dance floor, I have something sticking up out of it, and hopefully you can tell that that thing that's sticking up out of it is a square. And what makes it a square? Well, the square is based off of the distance from this top equation to this bottom equation, right? This is we'll call it the width of the square. But then the height of the square has to be exactly the same. So however long that space is, that one is there too. Now, notice though that the square doesn't have to be right here. What if I were to shift the square to the left a little bit? What would happen to the base? Well, hopefully you're noticing that the base has got to get smaller, right? The distance from here to here is much smaller than this one. So watch what happens when I shift the square to the left. You'll notice that that square starts to shrink. It's much smaller over here. Okay? And then if we keep going left, it's smaller and smaller and smaller. Now, the problem with a square is any individual square is only 2-dimensional. And even if you put 2-dimensional shapes right next to each other, it just makes a lot of 2-dimensional shapes right next to each other. So our goal is to create a 3-dimensional shape where anytime you cut it, think this vertical cut going up and down. Anytime you cut it, it's going to make this perfect square. So the way we do that is first we're going to take this square and we're going to give it a little bit of width. We'll call this dx. So I'm going to vanish the square over here and I'm going to give it a little bit of width here. So where are we? Oh, that's too many. Okay. Need to slide you over. Oh, there we go. That was silly. My computer's just going very slow. It doesn't like me using this program at the same time as, slide right, there we go, m equals 1, okay. So it doesn't like me using this program at the same time as I'm recording, but we'll see what I can do. Alright, here are a bunch of slices. Let's see what happens. Notice that each of these slices now are squares with a little bit of width. I'm just using 9 slices here. But can we see that each slice has a square in it, and this little bit of width here is just like our dx. Now you're like, that's kind of a really weird, ugly looking shape. Well, it is, because we only have 9 squares, but each of these squares right now actually has a set width. Each width looks like maybe it's about 1/4 of a unit, give or take. What would happen if we made the width smaller so we could fit in more squares? I think my computer is going to protest, but we'll try anyways. What would happen if I had, well, I don't know, let's do 19 squares. As I go to the right, you'll notice it starts to look a little bit more smooth, right? We're seeing this curve approach here. It's starting to be a really nice shape. It's fitting better inside the base as well. And so actually we should be able to see the full surface, which looks something like this. Now it's pretty difficult to see, but I can at least turn this a little bit and we can see the square sitting inside as well. It's actually a perfectly smooth shape, because if every square is infinitely small, it'll be very smooth to move from one thing to another. So to reiterate, first thing we do is we take this area, which we call the base, that's the bottom. Second thing we're going to do is we're going to build a square coming off of that base. That's two-dimensional though, so then the last thing we need to do is we need to give the square a little bit of width, and then we need to add up or sum up all of those three-dimensional squares. So let's get to it. Okay, a little bit easier to look with an example, I think. So, well, I really should have closed that program. I think my computer may have a tantrum too. So go ahead and move back to your worksheet and try to reread what we're doing, and I will close this out so this doesn't explode. Excellent. All right, let's get to it. So how do we do this? Well, the first thing I always like to try and do, and this is where you folks that like drawing get to have some fun here. You don't have to draw, but it really does help, and I'm going to ask you to try it, is I'm going to go ahead and draw a square that's poking off of the page at you. So I did the square in blue. Let's do the same thing. So here is a square, but that's only the base of a square. So this needs some sort of height over here, and then it's got to come off of the page. And that's not great. Could probably align this a little bit more. There we go. That one's pretty good. Okay, and you'll notice that we have our, our base down here, our height over here, and actually the base and the height are exactly the same in this case. So maybe we can use that cool geometry notation and just tick mark each one. Okay, but then, well, yeah, let's start with that. So there's my square. Step one, the first thing you want to do is you want to build your area function. And to build your area function, I'm actually going to redraw the square just like this. Okay, and we're going to figure out how we find the area, or the length and the width, and then eventually the area of this shape. Well, the base is just the distance from this function right here, which was the natural log of x, all the way down to this function right here, which was y equals 0. And we know how to find the distance between two functions. We did that last class. That's just going to be top minus bottom. So my base right here is just going to be the natural log of x minus 0. And the cool thing about using a square is the height is exactly the same, natural log of x minus 0. So now we have an area function. The area function is pretty easy. To find the area of any square, we just do the natural log of x minus 0 times, base times height, right? The natural log of x minus 0. So don't forget that the area of a square is just base times height. That's where those two came from. And then simplifying this a little bit, our area function is just really the natural log of x squared. Now, what does that do for us? Well, it tells us if we pick any x value, let's say we pick an x value of 2, if we plug 2 in here, it's going to give us this two-dimensional square, which is great, but what we really need is to find the volume function. The volume function is really easy once you've done the area function. The volume function is just take this rectangle or the square that's right here and give it a little bit of width, right? And we can do a little dashed line because we shouldn't be able to see through that. Can we see that little bit of width now? It goes up here, kind of goes over here, right? This width along the x-axis is infinitely small, so we call it dx. So then that means that our volume function is just going to be the area function times dx. Or writing this out a little bit more clearly, the area function was the natural log of x squared times dx. That means then if we again pick any one x value we want, let's say we pick 2 again, we plug in 2 here, it's going to give us the volume of this is kind of an abuse of the notation, three-dimensional square. So how do we find all of the squares that would fit in here, right? Because we would have more. This would be a much bigger square, something like this, right? And it too would have some sort of infinitely small width that would run across here, right? And then this would drop down and come across. Yeah, we'd add up all of these squares. Well, to sum them up, we bring in, of course, our integral. So the last part of this is we need an integral symbol. We're going to integrate our area function times dx. Where are we going to integrate from? Well, the start, which was 1, and the end, which is e. We want to sum up all the three-dimensional rectangles that are in here. So really that's from 1 to e, the natural log of x squared times dx. And that's it. In fact, for today, all you're really going to be doing is just practicing the setup. And it's going to be the same setup every time. Can you find the area of the two-dimensional? And then, can you multiply by an infinitely small width? Now, good news. We do have one more example to get through for today, but the base is going to be exactly the same. So go ahead and redraw that base. I'll do the exact same thing right here. All right, it looks like this, give or take. We had where it starts at 1, it's going to end at e, and it's kind of this curvy triangular thing, right? Looks like that. All right, well, how is this one different? Let's see. Using the same base, check. Set up an integral to find the volume of a three-dimensional shape whose height is created by rectangles that are perpendicular to the base and the y-axis. Well, these rectangles right here were perpendicular to the x-axis because this line right here crosses the x-axis at a 90-degree angle. But now they're telling us to create a shape that's perpendicular to the y-axis. I think that's going to be a shape that goes the other way. All right, well, let's see how this works. So if we take a shape going the other way, I'll do my best here. Let's draw a rectangle first. Let's see, the rectangle whose height is 3 times the length of the base. So it's really, really tall and not so skinny. I'm not going to do a good job of this drawing, but that's okay. Positive mindset, I will do a good job of this drawing. So here is my base. Here is my really tall height. And then here is my rectangle. Yeah, that was a little silly. It needs to end a little shorter. Here's my rectangle that's coming off. All right, that was decent. Okay, and if it's a rectangle, this is my base here, and this height is 3 times the base. Okay, and if you wanted, you could draw another one that's hanging out over here. You really don't have to. It's going to be really messy. I'll probably erase that. Yeah, so there's a second one if you wanted it, but we'll just deal with one. So 3 steps again, and the steps are, again, really, really easy. First step, you need an area function. Your area function we call a of x. I always like to redraw my shape. Hopefully better than that. Redraw my shape. We've got a base down here. Well, the base is the width between e right here and this natural log function. Okay, but now it looks like we're going side to side. That should ring some bells from last class. We need to do right minus left. E is easy enough because that's already easy. That's already x equals e. But my other function over here, and I'll do it in green right now, is y equals natural log of x, and I need that to be in terms of x equals something. but it's easy enough to get rid of that, just e to both sides, and now we have x equals e to the y. The graph of e to the y is the same as natural log of x. So how do I find my base? Well, I take the right side, which is e over here, and then we have to subtract the left side, which is e to the y. And then I think we're looking pretty good. That is the base. That would be the distance. It's always e minus whatever the x coordinate is from my natural log function. Okay, well, how do we find the height? Well, they told us the height is just 3 times the base. So I think my height here then is just going to be 3 times e minus e to the y. So then our overall area function, a of x here, is just going to be the base, e minus e to the y, times the height, 3 times e minus e to the y. And putting that all together, we could probably simplify this as 3 times e minus e to the y squared. Okay. Now, that's 2 dimensions. We need to give it a third dimension. So let's give my cute little rectangle here a little bit of dimensionality. And we can maybe see this poking off the screen at you. You'll notice too that this piece right here is now not along the x-axis. If you extend it out, it's actually along the y-axis. So the width of this base now is not dx, but my width is now dy. So my volume function, right, maybe I'll call it v of x this time, is just going to be a of x, which was 3e minus e to the y squared, that's 2 dimensions, times my third dimension, which is dy. So last but not least, I need an integral, and my integral is just everything we've done so far but put together. I need to integrate of 3e minus e to the y squared dy, but from what to what? Well, we need to be using only y values here. Everything needs to be in terms of y, and these are x values. So y values, well, the lowest that my area goes is 0, so that's easy. The highest that it goes, well, what is that point? Did we do it up here? Well, this point has got to be e comma something, but when I plug the something in, right, natural log of e is just 1. Oh, so this is just 1 up here. That's easy. So we're just going to go from 0 to 1. And there is our volume. Okay, so we have 3 practice problems. The first one is calculator active. The second one is no calculator. The third one is calculator active. Your job is to go through and see what you can do with this. And then once you've tried them, please try my second video for day 93.